5 minutes remaining. Oh my god, I still have like 3 questions left. Oh my god, I'm not gonna make it. That could be you if you don't follow my calculus videos. Hey guys, it's Final Exam Guy, and I'm back with a brand new exam for you guys. We're going to be going through the second portion of calculus where you learn about integrals in depth and summation and Riemann sums, all that fancy stuff. I got a nice final exam with about 12 questions to go through, and if you follow this from A to Z with me, you'll probably do a lot better than you would have if you didn't. So let's get started. So guys, a lot of people find calculus 2 to be a lot harder than calculus 1. I do agree that it is harder, but not really hard. You need to be good at spotting things in calculus 2. Like if we give you an integral, you need to know what to do. You need to figure it out pretty quick, because if you're going to be looking at it for an hour, you're not going to get through your final exam in a good amount of time. There's a lot of concepts to understand. We kind of do. Well, we don't touch on double integrals much, but we start looking at 2D figures. And we look at Riemann sums. We look at graphs of shapes, areas under the curve, and how to figure out the area of under a curve by using integrals and Riemann sums. What else do we do? There's some series to be done in calculus 2, of course. It's always going to come back. Taylor series, power series. Converge, finding out whether something diverges or converges. So it's more in depth than calculus 1, but you just got to practice a lot so you can be able to spot things really quick. So that's what I'm gonna help you guys with today. So I'm gonna try to go through each question as in detail as possible, so you understand what's going on in the problem. So we're gonna start here with question 1. Alright guys, so we see here that we have to find the integral of -3 minus 3 over 2x dx from -4 to 2. But we can't use traditional methods of taking the limits. We have to use the Riemann sum. I don't know if it's Riemann, but anyways, Riemann sum. And then we have to interpret the integral in terms of areas. So there's 2 methods to find the integral here. So they give us these formulas. These formulas should be given to you on the exam. I know I had a formula sheet on my Cal 2 exam. So I guess talk to your teacher. So let's start here with the integral. And I'm going to write down the formula for the limit of a Riemann sum, and we're going to interpret it, because it's not always easy to understand these formulas as well as notation. So we got to validate this integral, but first we have to write what it looks like. What it looks like to take a limit using Riemann sum, and this is the formula that you should be given on the exam. So the integral of any function dx is also equivalent to the limit as n approaches infinity of the summation I equals 1 to n of f of xi star multiplied by dx, change in x, delta x. So there's 2 things you need to understand that's going on here. We're taking the summation from I equals 1 to n of this term, this x of I star, we have to find it, and this delta x we have to find as well, and we're given formulas for that. So let's start by writing, and we'll go through what this summation means. We'll go one thing at a time. So let's we got to find our x star, and that's also a formula. And it's given by a, where a is your limit, your first limit of integration, plus delta x multiplied by I. And this delta x here is simply your limits of integration subtracted, b minus a, over n, and n is some is the top of your summation. We don't put a value for that yet. We don't need it, and it often gets canceled out later on. So we'll see what's going on. So let's calculate these two things, and so for our a is -4, and then we have plus 6. This over here is 6, so b minus a, so 2 minus -4 over n equals 6 over n. 6 over n times I. That's a, and that's delta x. So let's see what we do next. We're going to plug what f. Let's go back to green. What is f of xi star? So what you do here is you'll plug in every time you see an x. Basically, you plug in xi star. So this would be looking like the following: -3 minus 3/2, and every x becomes an xi star. So -4 plus 6i by n, and then we have dx. So we've set up our new function to look like this, and now we can actually plug it into this definition here, and it will be -4 to 2 of -3 minus 3/2 x dx is equivalent to the limit as n approaches infinity, the summation I equals 1 to n -3 plus 4 minus -3 minus 3 over 2. Well, we can plus 6 over here, minus 9i over n over 6 over n. If you lost me, I just distributed this, and then we get this as a result. So this ends up looking like, for just work on the right side, summation I equals 1 to n. So now if we distribute this 6 over n, we get -18 over n plus 36 over n minus 54i over n squared, which is equivalent to the limit as n approaches infinity of the summation I equals 1 to n of 18 over n minus 54i over n squared. Alright, now we arrive at a point where we're going to start to look at these formulas here. These three here, these four. A property of summations is that you can distribute them like if I can distribute summation to each of these, like I'll kind of multiply it into the brackets. So I will get what it will look like is this, because it's hard to take a summation of two terms here, 18 over n minus 54i over n squared. So if we can separate them into one each, it will be nice and simple. So it would end up looking like summation I equals 1 to n to 18 by n plus summation I equals 1 to n negative 54. I mean, I could just pull that negative out, but whatever. I. And now what will happen is that we'll... Alright, I brought the two formulas, the first two formulas they've given us. I brought them down here so we could see. We got to turn these summations into just we got to get rid of these summations. We got to apply these rules here. So let's go ahead and if we can make this one here, this first term, into this, look like this, where we just have some constant being summed, we will just get the constant times n. So if we can work with the first term, let's see what happens. Well, let's simplify both. You see here I have an I, and this second one here is the summation of I equals n plus 1 over 2. If I can just get an I in front of this summation, then we have this, and we can just replace it by n plus 1 over 2. So let's say here for the first term I bring out the 18 over n. Then I have the summation of just the constant 1, and that's right here. Summation of a constant is the constant is equal to the constant times n. And then if I can bring this negative 54 over n squared outside the bracket, 54 over n squared outside the summation, and I'll just have I here. So now we have both terms here in this form. So I can just rewrite this limit now as 18 over n, and the summation of a constant from I equals 1 to n is just a constant times n, so 1 times n, so just n here. And then the summation of just I is n plus 1 over 2, so I'll have minus 54 over n squared n plus 1 over 2. Right, now we just we killed it. We just made it in a simple form here, and we can further reduce this to 18, the n's cancel out, and minus 54 over n squared, and then you can multiply these this n into the brackets, so you have n squared plus n over 2. And this further reduces to the limit as n approaches infinity of 18. Now if I distribute this 54 over here, I'll have 54 n squared plus 54 over n squared, and 2n squared. And this further reduces to, because you can distribute this 2n and then cancel stuff out. You can separate these numerator with a piece of the denominator. To infinity, 18 minus, you get something that looks like this. And now you could finally evaluate your limit right here, because if you do plug in your infinity, you get 27 over a very large number, which goes to 0. As opposed to if you were trying to do it here or here, it's just a mess. Like you got to further simplify. And I told you in the beginning, like this stuff like n squared gets canceled out, so it leaves something really simple at the end. So if I take the limit, this goes to 0, so I'll get 18 minus 27, and I'll get negative 9. Simple as that, guys. It's a lot of work there to show there, but guys, you gotta do it. Take it one step at a time, and you'll be fine. So question B asks us to interpret the integral in terms of areas. So we can actually find the area of this integral by just plotting what it looks like, and then we pretty much have to take the area under the curve. So our function, our original integral, was from negative 4 to 2 of negative 3 minus 3 by 2 x dx. Alright. So our function here is we're working with is this one here, negative 3 minus 3 by 2 x dx. If I can plot it, I actually just have to take, it ends up looking like a triangle, because you see this is just a y equals mx plus b type of equation, so slope and intercept. So let's go ahead and plot it here. So what are my knowns? I know that it passes through negative 3, because this is the y-intercept, and the slope is negative 3 over 2. So we'll pass through negative 3. my bounds of my integral is from -4 to +2. That's where I'm bounded by. That's where I want the area. I don't want it to pass. Sorry, I don't want it to pass this this bounds. We need to find the where it intercepts the x-axis. So we'll put in we'll set -3 minus 3 over 2x equal to 0, and we'll find that x is equal to -2 from this. So it will intercept here at -2, and if we just plug in our bounds, we can see what we will get out of it from it. So let's see. We'll plug in f of 2 into here, and we will get back -6. And if we plug in f of -4, it'll spit back 3. So we can put those points on the graph. So f of 2 is all the way down to -6. We'll say it's somewhere here. So we got a point here, and then f of -4 will give us 3. So we got a point here. So our slope, our line is passing, starting here. This is the outermost bound, passing to -2. It's not looking right, and it's supposed to pass through -3, and then up there. Not the most accurate drawing, but I mean, let's see what I can do to fix it up really quick. This has got to be this has got to be -3 over here, and this here, it's got to be -6 over here. This here has got to be -6. So let's say our graph looks like this, and our slope m is -3 by 2x, and we just need to find the areas of the curves, and these are the areas of the bounds is here, -4, and the bound is 2 over here. So we got to find this curve area and this curve's area, and these are just simple triangles. So let me just write the equation down. So the integral of -3 minus 3 over 2x dx from -4 to 2 will just be two triangles, and any triangle below the x-axis is going to be a negative area, and the one above is going to be positive. So if I take the area of this first triangle, and we know that the base is from -4 to -2, so that's the length of 2 times the height. So we know that we're going from 0 all the way to 3. Divide by 2. That's base times height over 2. That's the area of a triangle. And then we subtract because it's below the x-axis, so it's a negative area. And we know that the base is from -2 to 2. That's the length of 4. And the height is 6 from this point to that point. That's the bound, 6 over 2. And we get -9. So do we get something similar to the other answer? As a matter of fact, we get the exact answer. Same thing. So that's two methods of finding it. Riemann sum is more analytical, but it's doing exactly the same thing as taking the area. Just you can't really see it. It's abstract a bit. So that's question 1. Sorry. Let's move on. Trig substitution, a feared term among calculus students. I hated doing them, but after a while, I just realized now it's really easy, guys. It's all about spotting it in the beginning, and then you can work with it. So question 2 is evaluating a few different integrals using various methods. So look at the first one. It's 1 over 9 plus t squared 3 by 2 dt. You should be able to recognize that it's trig substitution. This comes with practice a bit there, but if I show you what the rules are for trig substitution, you'll catch it right away. So anytime we have something looking like this, where we have 1 over some constant plus a variable squared raised to the n, and it looks like one of these three forms over here. So form 1, a squared minus x squared to the n, where a is a constant. You would make a substitution for x where a is equal to sine theta and dx is equal to a cos theta d theta. If you have it in the form a squared plus x squared to the n, your substitution will be x is equal to a tan theta, where a is the square root of a squared, right? Then you'd have dx is equal to a secant squared theta d theta. And if it is the form x squared minus x squared, and x is equal to dx is equal to a secant squared tan theta. Alright, ours is in the form of number 2 here, obviously, where a is equal to 3, square root of 9. But it's not always going to be that obvious. When you get on an exam, you might get it like this, where it's obvious right away, but you might just get it in a more complex form where you'll have to manipulate it to make it look like one of these three forms. So I wish you all the best with that. Depends on your professor, if he's hardcore. But yeah, I suggest that when you see an integral that you're actually having to evaluate, you run it through your head, you run through each method. Which one should I use? Which one does it look like? Is this a good candidate for regular substitution, trig substitution, integration by parts? You'll see. You'll catch it with time. You guys got to keep practicing. So if I go ahead and make the substitution here, 1 over 9, and our form is number 2, so we would put, for t, we'd put plus a, well, a is 3, sorry, 3 tan theta squared to the power of 3 over 2, and this is squared, right? Forgot to put it there. And dt would be plugged in a secant squared theta d theta. So we would have it looking like this: 9 plus 9 tan squared theta times 3 secant squared theta d theta. Alright, and all of this denominator is raised to the 3 over 2 still, don't forget. I could pull out this 9 and factor it out from both terms. I would get something like this. Nine times 1 plus tan squared theta, right? And what we're going to have to try to do in trig substitution is cancel some terms out. So you can see that there's a trig identity going on here. 1 plus tan squared, 1 plus tan squared, so basic trig identity is equal to secant squared theta. And again, I forgot the 3 over 2 here. So if I can replace this 3 over 2, this 1 plus tan squared by secant squared theta, I would actually get something we can cancel out with the numerator. So replacing this with this, distributing this 3 over 2, I get the following: 3 secant squared theta d theta over 27 secant cubed theta. And if I pull out the 3 over 7, which is 1 over 9, I get 1 over 9 integral. I cancel out the secant squared, and it just leaves me with a secant on the bottom. 1 over secant theta d theta. which is now just a simple integral, 1 over 9 integral cos theta d theta, and that is 1 over 9 sine theta plus c. Don't forget the constant of integral because it's an indefinite integral. We're not given any bounds. There's just one last step here. Our original problem here is in terms of t, variable t. We have it in theta, so we gotta figure out how to get it into terms of t. So we called our original t, we had called it 3 tan theta. So now if we can isolate for theta, we have an answer for it, right? Theta is equal to t over, tan theta is equal to t over 3. And at this point you draw your triangle, you draw your right angled triangle. And you know that, here's your theta. Tan theta is SOHCAHTOA, so opposite over adjacent, opposite over adjacent. So your opposite in this case is t, and your adjacent is 3. So you basically just have to find your hypotenuse, which is 9 plus t squared. And we know that our answer is in sine, right? So sine theta is opposite over hypotenuse, which is t over root 9 plus t squared. So I can just replace this for here, and I have an answer in terms of t. So our integral is equal to 1 over 9 times t over root 9 plus t squared plus the constant. It's a lot of work. Calculus 2 is a lot more work. But here's our answer for part A. And now we'll move. Alright, so part B looks pretty intimidating because you have 3 different terms going on here. 3x squared, sine squared, cos squared of x cubed. But once you see it, you'll be like, oh, there, I got it, no problem. But it does get harder after because of identities that you need to figure out, trig identities specifically. Well, we'll go through it one step at a time, and hopefully you'll be able to point it out on an exam of what to do. Alright. Another famous method of solving integrals is regular substitution. Is where you take one term and you call it u, and then you take its derivative and you solve it that way. I don't know why I put x sub 3 over here. It's cubed. My bad. Alright, so usually substitutions is when you make a substitution with some variable u and you take its derivative. You'll be able to replace this dx with the derivative, and you'll see what I mean now. Look, let's say we call u, our substitution, we call u is equal to x cubed. Then we would take its derivative. We see that it's 3x squared dx, which is exactly what you have here. That's what often happens in substitution, is whatever you substitute, and when you take its derivative, you can sub what's left over in the integral with the du. So like if I rewrite this, 3x squared dx gets replaced by du, and sine squared x cubed and cos x squared x cubed get replaced by sine and cos squared of u. So you'll see that we have sine squared u, cos squared u, and du. It's a lot simpler now, but we still don't know what to do here. What do we do? This is the tricky part. I mean, you gotta be sharp at this. It comes with practice again, but you see trig terms here. You gotta think identities right away. You gotta be able to replace this much simpler. You gotta use the for this one you use the power reducing trig identity, where you can take a sine squared term and replace it with something much simpler. What I'm referring to is this identity right here. Sine squared of x is equal to 1 minus cos of 2x over 2. And also cos squared has 1 as well. Cos squared x is equal to 1 plus cos 2x over 2. You see that by replacing these into there, we now have a cos term with no power on it, which makes it that much easier. But we still got a little bit of work to do here, so let's go ahead and put this in here. We sub in 1 minus cos 2u over 2, first term, and we multiply by 1 plus cosine 2u over 2 du. They have the same denominator, so we can just put them all on one fraction. So we get 1 minus cos 2u, 1 plus cos 2u, and over 2. I mean, it doesn't matter whether they have the same denominator or not. I'm just I made a mistake. We're just multiplying them out, right? Numerator times numerator over denominator times denominator. It's not an addition, so it's not common denominator. So now if we go ahead and use FOIL method to multiply these two brackets out, we would get 1 plus cosine 2u minus cosine 2u minus cosine squared 2u over 4. We see that this cancels out, this cancels out. We get 1 minus cosine squared u. And now we're back at it looks like we're back to square one here, because we have a square over here, and we're back to having another squared in a term here. But it doesn't matter, because we're gonna end up using another identity here shortly. So look, if you see that we can factor out this 1/4 here, we'd be left with 1 minus cosine squared 2u du. Now it's looking nice. We got rid of the fraction, and we can just convert this. We know that the identity 1 minus cosine squared x is equal to sine squared x. So if we have cosine, and there's a 2 over here, I forgot to put a 2, and there's a positive here, I don't know why I put negative. This, we can follow this identity, we would get the integral 1 over 4, the integral of sine squared 2u du. And once again, we have the reduction of powers identity, this one here, except that this term would now be 4u, because we have a 2u in here. So we would get 1/4 integral 1 minus cosine 4u over 2 du. And if we factor out that 1 over 2 term, we get 1 over 8 integral of 1 minus cosine 4u, which finally gives us an integral of u minus 1/4 sine 4u plus a constant of integration. This integral is really simple. I mean, this just becomes u, and this becomes sine, and you just divide by the inside, which is 4. So now we can plug back in what we established our u was. We established our u as x cubed, so we can plug back in everything. X cubed minus 1 over 4 sine 4x cubed plus c. And that is the answer. Alright guys, that concludes part 1. Be sure to check out part 2. I posted it at the end of this video. Don't forget to like and subscribe and share the videos to share the knowledge. I'll see you guys in part 2.